This is nerve-wracking. So as the first day of graphing some more complicated shapes with polar equations, one of the things you need to know is that we're not going to be converting these into rectangular coordinates. We're going to be operating entirely within polar coordinates. So the second thing is that I'm going to be flipping back and forth between the page that has 6 per page. That's going to be the easiest of the two to actually graph on, and the notes here. The page that has 2 per page is there for you to see and use if you want a lot more detail. So some of them that are coming will have multipliers in front of the theta. That means that you're going to be graphing that many times as many points. So it can be helpful to have them down this far. I do want to look at this for just a second. This particular one, it's broken down into, well, if you kind of think that, if I were to kind of label this, something that to make sense of this would be, at the very least, putting down what your axes are. So there, and then I put it like a half mark there. And I would do that on all sides, because then that visually helps me get a sense for where I am. And then beyond that, let's put the vertical down here, and put that one there. So that helps you see where the 45-degree angles are. On an axis, I would kind of sometimes do this, where I put 1, 2, 3, and 4, and let it be 4 across or 4 out. That way, if you scale this to 4s, it's not too bad to deal with. So this can help you get a sense for what's going on. And I think already it's becoming a little bit more clear than it was before about what kind of thing you have and where they are. You can also put these marks here and here that indicate your 30 degrees and your 60 degrees. But then knowing that this is 15 degrees means that every one of these is 5 degrees, right? And I think you can do the math where if this is pi over 6, this is pi over 12, which means that this would have to be a third of pi over 12, which means it's pi over 36. So if for some reason you got to something that had pi over 36 as the unit, you could use this to kind of help graph those very, very, very tiny increments that happen. So that's there, again, purely as a reference. I gave you 4 of them on each page, front and back. You're welcome to grab any more of these pages that you'd want for homework, or find your own. And you can, honest to God, Google polar graph paper and find your own, and if you want to. These files are also at the top of any of these that I've attached. So right there, that's a PDF. Open it up, print out some more. You've got tons. I've got that for the 2 per page and for the 6 per page. I will be operating off the 6 per page. I'm going to put number 1 here. This is going to be R equals 2 plus 2 sine theta. Do not T-chart on this page. There's not near enough space. So I'm going to flip over here and do the same graph and start T-charting some values. And you're going to get a sense for what this looks like. I would like to challenge you not to cheat and look at the graph before starting. You're trying to learn how to do this. And working your way from the backwards or from the end to the front may actually be counterproductive when it comes time for a test or something to do these. I also am not going to give you ones that take a stupid long amount of time. I don't want to do that on test or quiz. We're going to have a quiz in 2 days, 2 class days, so not tomorrow, but the day after. It's going to have 1 or 2 of these, and they're intended to be relatively quick. Probably 1, because I have some other things I want to do that day. But that's just to hold you guys accountable to learning how to do this. So, how do we do this? I'm going to build a T-chart, but I'm going to build it in 3 parts. You can do as many parts as you want. I'm just going to try to do it to minimize some brain power. I'm also going to do this without a calculator as much as possible, meaning I'm going to try to do it without the use of a 4-function calculator or one with radicals. So the 2 approximations we're going to use are radical 2 is about 1.4, and radical 3 is about 1.7. We aren't going to need to graph more than just tenths, and we really can't with our little tiny fingers, but, you know. Here we go. Theta is going to be our input. Then I'm going to do sine of theta because, you know, you're still learning trig to an extent. I'm assuming that trig is fresh in your head, and if I ask you the sine, cosine, and tangent of any of the angles that we've ever done, you can get them in maybe not 2 seconds, but at least 10 seconds, given that you can sketch the triangles and do them. If you need to sketch triangles, do that. I will be doing it as we figure out all the different values that we need for these. But don't get those wrong. Like that's so elementary now. You know, we've been doing trig all semester. It's sort of like being at the end of third grade and knowing that 3 times 5 is 20. Like we should be able to move beyond that at some point. So we have to presume. And if trig is the thing you need to review, then review it. You're going to have to for the final exam anyway. No, I know 3 times 5 is not 20. You're kind of looking at me, am I serious? That's a joke. The next one is 2 plus 2 sine theta. And I'm going to draw vertical lines down. And so, okay, here we go. I want to do this until I hit a pattern. A pattern eliminates the need to do any more. So, given that, let's just start with our first theta, 0. And the sine of 0 is 0. And 2 plus 2 times 0 is 2. 0, 2 is a first-ordered pair. I'm going to split screen and get this to show that so that I can actually start to graph this kind of live here. Given that I'm using the smaller ones, I'm going to do it in a 1-to-1 scale where I'm actually showing what I'm graphing. So here we go. 0, 2 is that point. Angle of 0, radius of 2. Now, when I did this before, I really wanted to be careful to make my dot small, so I'm going to try to make my dot somewhat small, and we'll keep moving up. My next angle is pi over 3, kidding, pi over 6. The sine of pi over 6 necessitates that you draw this triangle if you really want to get it well. What's the sine value? 1/2. Remember, 1, 2, root 3. And then 2 plus 2 times 1/2 is 2 plus 1, which is still 3. So pi over 6, 3 is now an ordered pair. And that moves out there. Next is pi over 4. The sine of pi over 4 we're going to write down as root 2 over 2. And then we're going to approximate that. Half of 1.4. 0.7. Actually, may not need to do that because I'm immediately going to do 2 plus 2 times that again. So that's 2 plus 1.4, or 3.4. Where is 3.4? A little bit under 3.5. So we'll put a dot here and then continue. Pi over 3 is root 3 over 2. I know root 3 is 1.7. So 2 plus 1.7 would be 3.7. I'm going to put a dot out here. And then finally, for this set, pi over 2. Sine of pi over 2 is 1. That's vertical. 2 plus 2 times 1 is 2 plus 2, which I think is still 4. And I'm going to put an ordered pair at pi over 2, comma 4. Are there any questions right now about where I got any of these 5 points? Simba?
How did you get the theta values?
I'm picking them because I know where to graph those. I know what the signs are of those. Those are basically the ones we worked with all last year, or last semester, this semester, wherever we've been. God, feels like it's been a long semester, at least for me. Okay. What I'm going to do now is a little bit controversial. So many ways to take that one. I'm going to now skip over from pi over 2 back to pi. And you guys are going to smile and say the sine values of the angles between pi over 2 and pi are exactly the same as the ones we just did, right? The sine of these angles, because sine is positive in quadrants 1 and 2, if I start cycling through quadrant 2 now, I should hit exactly the same values. Which means, where are these going to be located on this graph? What points am I going to graph? Can we use the word reflect? and we're going to reflect about, yeah, it's not the y-axis anymore. Sorry, guys. They were in r's and thetas. It is the y-axis, but we call it, I know, it's a cheapy name. We call it the theta equals pi over 2 axis. It's the vertical axis. Yes, every one of these points is now going to be the same point over on the left. And as pi over 2 travels to pi, this 1 becomes a 0 again, and the 4 goes back to 2. Which means that pi, the angle of pi, now has an ordered pair. I really want my draw up 2. And every one of these points we did is now reflected, so I'm going to work my way in reverse and just really try to be careful and hit up this same point. And then that point, 1.7. Okay. Whew. Got those up. Let's continue. Because crazy new things happen in Quadrant 3. As soon as I start graphing into Quadrant 3, and it may be helpful to list the values now before you get going, 7 pi over 6, pi over 3, 2 pi over 3, 4 pi over 3, oh, but I forgot my 5 pi over 4, 4 pi over 3, and 3 pi over 2. Man, how amazing you guys have gotten at fractions just from this. Keep those going down. The sine of 7 pi over 6, well, you can travel, again, the same road you did up above and just make these the negative ones. Negative 1/2, negative root 2 over 2, negative root 3 over 2, and negative root 4 over 2, which I just call negative 1. And now the math, 2 minus 1, then 2 minus 1.4, should be 0.6, then 2 minus 1.7, and then 2 minus 2, 0. So right here on the first quadrant, pause for a second. What this is doing is it's saying we're going to start here, and I'm going to move this radius out to 2, and then move it right back down to 2. Now I'm going to move the radius to 0, and then move it right back out to 2 again. That's what this is doing, this new set of t-chart values that we've just done. My radius is going from 2 down to 0. So let's plot those as best you can. This means I'm going to zoom in. Really, to get a look at this, you can just look closer. The next radius value is 1, then 0.6, do the best you can, then 0.3, which is half of 0.6, and then 0. What do you think Quadrant 4 is going to do? Exactly the same values, because the sine of angles in Quadrant 3 is the same as the sine of angles in Quadrant 4, and it's just going to work your way back out. So you might as well graph them again while we're kind of on a roll here. And I get those going. Okay. Zoom out, and now the victory lap. Like the animated part of the graph that I was showing you guys with parametric equations, this is a motion. This is the motion of graphing this. So do the best you can. Pencil starting at any point. And one smooth motion out. I would lift your pencil after every single quadrant you do. Uh-oh. So I'm not quite getting this just right out there. There we go. Okay, that's about as good as I can do. This shape has a name. It's called a cardioid. There have been other names that have been proposed for this. It's called a cardioid because it looks like a... I was going with heart, yes, cardioid means heart. But some people think this looks like another object or another part of the human body. So they proposed some other names for it. I'll leave you to wonder what names those might be. We should probably, on a video that's going to be posted to YouTube, refer to this as a cardioid and not any other oid that could be prefixed to show other shapes that this could be. So for more on that, you can check out period 1 where we did say those names for fun. But you guys want a recording. I'm shaming the people on the other end of this recording and making them wonder and feel bad. Not really. I'm sure they I don't care. Okay. So that's a cardioid. Let's move on to the next one. R equals 3 plus 2 cosine of theta. Now, I want you guys to look at this and practice scaling a little bit. Scaling means what's the biggest radius that can possibly come out of this and what's the smallest radius that can possibly come out of this. What's the biggest that 3 plus 2 cosine theta could ever be? 5. Because cosine theta can be at most 1. What's the smallest it could ever be? That's when cosine is 0. Now make cosine negative. 1. 3 minus 2, right? Because the smallest cosine can ever be is negative 1, so 3 minus 2 is 1. Your radius is going to go from 1 to 5. It's going to go from 1 and back out to 5, and then 5 back to 1. So that's sort of a sense of what this is doing. It can kind of help you visualize this a little bit. Just a little, I imagine. I'm going to do this on the second slot here. R is equal to 3 plus 2 cosine of theta. And I'm going to do this on a graph that gave me 4. We can do a fifth. We'll be okay. We'll go off page for just a little bit, but we sneak in a fifth one just so I don't have to change grids. Okay, here we go with our T-chart. Theta, cosine of theta, 3 plus 2 cosine of theta. Let's put down our values. 0, pi over 6, pi over 4, pi over 3, pi over 2. Cosine is positive in quadrant 1, but cosine is negative in quadrant 2. So I'm going to keep these values going for another quadrant until I get to pi. 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. It's sometimes helpful to do all of these at once just to get the patterns going and you don't have to think too hard. Cosine of 0 is 1. Cosine of pi over 6 is root 3 over 2, root 2 over 2, root 1 over 2, which I call 1/2, and root 0 over 2. And then you move to the negatives. Negative 1/2, negative root 2 over 2, negative root 3 over 2, and negative root 4 over 2, which I call negative 1. Then 3 plus 2 times these isn't too hard once you've built these up. 3 plus 2, 3 plus root 3, 3 plus root 2, 3 plus 1, and 3 plus 0. Then 3 minus 2, 3 minus 1. And 3 minus 1.4. Then 3 minus 1.7. Then 3 minus 2. Do you see how this already feels a lot quicker than what we did before, even though it's about the same kind of problem? You will get better at this. And then we plot. These are all different radii values, so we're going to plot all of these, starting with 0, 5. I'll just put right there. Then 4.7. I'll put there. Then 4.4. Then 3. Then 4, then 3. And then I'll carry these down on the next one. Then 2. Then 1.6. Then 1.3. And then 1. What do you think the points in quadrants 3 and quadrants 4 are going to do? Don't jump out all at once on this. Yeah. In quadrant 3, you have exactly the same values as you had in quadrant 2, because both of those are the quadrants where cosine was negative. In quadrant 4, you have the same values you had in quadrant 1. It will reflect about, we don't call this the x-axis, we call it the polar axis. It's the axis where you change from positive radii to negative radii, but it's still the x-axis. So I'm going to zoom in and do my best to kind of work my way back out. If you're really careful, you can kind of use vertical lines to make sure that you're aligned up with where you are. And then that goes here. And I have the next one kind of out almost here, and the next one just a little further out. And I think I've got all of them down. Then you connect. Got it? This has a very peculiar name. It's not centered at 0, 0. It has a name called a limaçon. Oh, that should go the other way. I never knew how to say that until one year I just asked, went on dictionary, Googled it, and then hit the play. And it's like, limaçon. Okay. It's a limaçon. You do not have to know the names of any of these. I'm just letting you know what they are. Okay, number 3. We have 4 major ones we're doing, and it may be time for a 5th, so hang tight. R equals 1 plus 2 cosine of theta. Can one of you tell me what's different about this one versus the other ones that we've done? There's a major difference that's going to happen here. What's the biggest at the radius, smallest at the radius? Luke? Yeah, R is going to become negative here, which means you're going to have a little understanding of what happens when R is negative. Fortunately, you guys rocked the factor out of your homework yesterday, or 2 days ago, whenever we last met. Is it Wednesday? Tuesday. I haven't seen you guys since Friday. Oof. I know, it's only Tuesday. Okay. Theta, cosine of theta, 1 plus 2 cosine theta. Same theta cycle, so lo siento, 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. I almost half apologize. I was tempted to copy paste the left side of that from up above. I should have. but I'm not going to do that to you. Yeah. Okay, cosine of 0. Then we have 3 pi over 2, or root 3 over 2, root 2 over 2, root 1 over 2, root 0 over 2, negative 1/2, negative root 2 over 2, negative root 3 over 2, and negative root 4 over 2. And then we're going to do 1 plus 2 times each of these. 1 plus 2, 1 plus root 3, 1 plus 1.7, or 2.7. 1 plus root 2, which is 2.4. 1 plus 1, still 2. World's not broken yet. 1 plus 0, 1. Take a breather. Move on to second quadrant. Here we go. 1 plus negative 1. 1 minus root 2, which is 1 minus 1.4. Then 1 minus root 3. Then 1 minus 2. So how you graph this can get a tad bit tricky if you don't know what you're doing. But you guys do. We hope. Start graphing. 0, 3. 1, 2, 3. Put a point. Then 2.7. So find halfway and go just a little bit to the right. Then 2.4. Find halfway and just a little bit to the left, but kind of closer. Then 2. Then 1. That first quadrant's not too bad. We're cycling back from a radius of 3 to a radius of 1. The next point is tricky. 2 pi over 3, 0. Actually, anytime you see a radius of 0, you're just back at the origin. Then 3 pi over 4, negative 0.4. So that means we're going to the angle 3 pi over 4, but we're flopping over to the other side to put that negative 0.4. This is 0.4 over in quadrant 4 along the 7 pi over 4 ray. Then 5 pi over 6, negative 0.7. Okay, I really want to make that tinier. Negative 0.4, negative 0.7. And then pi, negative 1. Pi is to the left, but negative 1 is to the right, and we go back to here. Okay. I am going to connect this now a bit prematurely to show how this is being drawn, because it's being drawn exactly how you plotted the points. Go like this, then like this, and we loop back like that. I just want to say I did that in one motion. Thank you. Where do you think the next set of points are going to be plotted? They're the same points because it's the same values, just reflected. So let's do that and reflect these. Meaning we were at 0.7. I know I just kind of drew over them. 0.4, 0, 1, 2, 2.4, 2.7, and then back out. And when you sketch it, you're just continuing the shape all the way back out to where you started. Oh, that could have been better. Yeah, I'll leave it. And there you go. It does a loop-de-loop. The inner loop happens when you have a negative radius because you're popping over to the other side now. The name for this This is called a limaçon with an inner loop. Technically, the other one was a limaçon without an inner loop. How are you guys doing? I know. Let's do one more, and then I'm going to pause the video for just a minute. And we'll take a breather, and we'll do a fifth one. R equals 2 cosine of 2 theta. These are different. This is a whole different shape here. I think these are pretty. Okay. The 2 theta is going to make this tricksy. It will. It will make it quite tricky to the point of where there's some things that we may not completely be able to grasp. I'm also going to slightly change this on you guys, and I'm going to do this one on the polar graph paper we just said we weren't going to use. Not full screen. We're going to use the more complicated one. This will be good because it'll give you practice in using this one, but it also will enable you to show when you have something that's a little bit more complicated, how it can be, we can just kind of use this to characterize that. So, did I just, oh no, I put it on the second page. Okay. If you're flipping through notes, this is on the second page of the two. I don't know why I did that. So this is going to be R is equal to 2 cosine of 2 theta, and I'm going to separate everything out like you see here. You can get lost in the image if you're not careful, so just plot this on your own paper as best you can. I'm also going to put the tick marks here, 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 and here, and here, and here to really kind of show what everything is that we know. Okay, let's start with the T-chart. Theta, 2 theta, and then we're going to do 2 cosine of 2 theta. This is a little bit different, but I'm specifically separating out theta values and 2 theta values. Do you guys remember back when you solved equations with 2 theta, how you often had double the number of solutions because you had to anticipate that? I'm starting with 2 theta because that's what I'm actually taking the cosine of. So we're going to do 2 thetas all the way up to pi. So 0, pi over 6, pi over 4, pi over 3, pi over 2, then 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. Those are what 2 theta is going to be equal to. And then we get to go back and forward a little bit. So I'm going to go backwards now to what theta is. If those are 2 thetas, then what are thetas? Well, if those are 2 thetas, thetas are half of those. So this is 0, pi over 12, pi over 8, pi over 6, pi over 4, pi over 3, 3 pi over 8, 5 pi over 12, and pi over 2. Now I'm going to flip over to the right side and do 2 times the cosine of each of these. 2 times 1. 2 times root 3 over 2 is about 1.7. 2 times root 2 over 2 is 1.4. 2 times 1/2 is 1, and 2 times 0 is 0. These just now become the negatives. Negative 1, negative 1.4, negative 1.7, negative 2. That wasn't too hard. I'm going to try to convince you that if you really detailedly do this for one quadrant, you can logically figure out where the rest of them are. Ready? We have twice the number of points to graph. This is why we picked the more detailed of the two. 0, 2. So I'm going to start and put a point. Pi over 12, 1.7. The pi over 12 is the major indents that you see. The pi over 36s are the minor ones. So pi over 12, 1.7. This is also separated out into every 0.2, so you actually should be able to get 1.7 pretty well. 2, 4, 6, it's halfway in between. There's 1.7. Kind of neat that you actually get this precision. Pi over 8, 1.4. This can be weird, but it's not impossible. Isn't pi over 8 half of pi over 4? It's not a ray that's actually visible here, but it should be right here. If this is pi over 4, pi over 8 is that tick mark. So we can put 1.4 there. Oh, wait a minute. I graphed 2.7. Yeah, where you guys are? Okay, there's 1.7. We'll put 1.4 right there. Then pi over 6, 1 is right here. Then pi over 4, well, I said anytime you see a radius of 0, you're back down. Then pi over 3, negative 1, this is going to get a little tricky. And this is where zooming out may help, because if you try to trace a ray through that middle where everything's condensing, you may lose it, and you may latch onto the wrong one. Straight edges do help, but I think it's just a matter of zooming back out, looking at the big picture. Pi over 3, negative 1 should appear right here. Yeah, that should be right there. And then 3 pi over 8, well, 3 pi over 8 is halfway between pi over this one. It should be right here, where I'm trying to aim for. If we keep the patterns going, that's where it was. So 1.4 would be right here. Then 1.7, and then negative 2. Okay, I'm going to zoom out and get this going. So the fun part is going to be sketching this. Now, let's play logic here, because this is like a repeatable unit that's going to be repeated throughout the entire object. So, can we do the next set of points and logically predict where those are going to happen? Where are they going to go? Wouldn't they just reflect here? Then out here? Then right here? And then take you back to 0. And without actually drawing this, doesn't it make sense that the next set's going to pop up in here? So if you can graph those, awesome. The partial points aren't completely necessary, but the major ones are. Now, another way to check that is to check these points and just move them over here, because they should be the same corresponding points that you had. So we'll put a point here. Then we'll put a point inwards and up on the 1.4, and then on that line at the 1.7, and then back out. This is a lot of very fine drafting that you're doing. And then we'll connect. Oops. Did not want to make that color. There we go. How do you think this object's going to finish? Do you notice how we've done 2 different curves now? We have 2 more to go. Does it make sense to you? Watch that you're going to do this. Something like that. Isn't this pretty? I know. And so I'm going to put the rest of the points down, and you guys can too. Let's just throw the rest of them down, because we have points to place. So there, then outwards would go here, and then I had one right here. And I'm really just trying to reflect these points that I already have about axes to try to get them exact as much as I can. I know. It can give you a little bit of headache if you do too many of these at one time. But this is about as complicated as they're going to get. So, see, this one goes inwards, not outwards. In, then in, and then back. And then up here, I've got to get these points going. So there, and there, there, and there, and then here, and here. And now I have my guide points. And now I'm going to finish sketching. You could continue putting ordered pairs down if you want. These are not the negative versions. This is all one cycle of it, all back on itself. Every two curves that you drew was essentially one quadrant. This was quadrant 1, this was quadrant 2, that was quadrant 3, and then this was quadrant 4. Remember, your points got doubled, so there's a lot of detail in a graph like this. That's probably the most detailed one I've drawn in years. I'm not kidding. A lot of times what I'll tell students to do, and this is up to you if you want to summarize this, that's about as detailed as you can get. The pi/8 points you don't completely have to draw. You've got enough information without them to get the shape going. And since pi/8 tends to be a very fine one to get, and is never marked on these things, you don't absolutely have to do that, but it's up to you on the detail you want. This is called a rose. This is a rose with 4 petals. Now, there's some caveats, or should I say thorns, in this rose. Every rose has a thorn. I want you to predict how many there would be if I made it 6 theta. This was 2 theta, and the 2 acted as an amplitude. So I'm going to do 4 just to make it bigger and kind of move it out here. And let's go to projector mode so you can see this. But 4 cosine of 2 theta. Here's theta, and there's 4. And let's put a slider in there so I can actually 2. There we go. Step of 1. Okay, and we'll make this out to 100. There's 2. How many do you think there are going to be if I make it 6? Or sorry, make this 3. Oh. What about 4? What about 5? What's the rule? Yeah, even ones get doubled, odd ones the same number. So 101, that's actually 101 different petals. But 102, that is actually 204 different petals. I'm not going to make you do that many. Now, if you're really curious, this is what 5 looks like. So, of course, I wanted to know what 5.1 looks like. It offsets just enough that it's taking 10 cycles to get back on itself. But you can see there's 5 distinct petals there. It's kind of a neat shape for me. And then like 5.2 starts to have some evenness. 5.3, 5.4, 5.5, 5.6, 5.7, 5.8. And we start to have that like getting closer to even or odd, and then you get to 6. And 6 is with 12. So you can play around with those. And I do like playing with these. These are fun. Okay, we're going to stop there. That's plenty, and we just did that for 45 minutes. Good Lord.